Welcome back. Well, after we have investigated differentiability from the point of view of difference quotients, as well as from the point of view of differentiation formulas, there is yet a third way in which differentiability can be investigated for functions of a complex variable, and that is through the Cauchy Riemann equations. So we're going to talk about the Cauchy Riemann equations. We're going to talk about those equations in polar coordinates. And once we have these results, we will derive some consequences for analytic functions. Remember, analytic functions are complex differentiable functions. And we're going to talk about functions that are called harmonic functions. Those are functions so that the sums of their second partial derivatives are zero, and those functions are very important in applications. Now, the proof of the Cauchy Riemann equations will be probably the most technical proof that involves difference quotients in this course, and the proof for polar coordinates will require a lot of coordinate transformations. So on one hand, we need to brace ourselves, but the good news is, of course, that these are good exercises, and the other good news for you is that this is the last really technical proof, at least for a while. And the good news for me is that after we're done with polar coordinates, I'm going to eat lunch before I'll talk you through the analytic functions and the harmonic functions. So let's take a look at this stuff. Basically, even though all the computations for differentiability work rather well with complex numbers, we've seen that those computations really were just the same computations as what we did in for functions of a real variable in calculus. It would be nice to also have an idea what complex differentiability means in terms of real functions of real variables. And well, the Cauchy Riemann equations provide just that. And as such, we will obtain a new way to look at complex differentiable functions and a new way to look at certain real differentiable functions, namely at the real differentiable functions that satisfy the Cauchy Riemann equations. Finally, and that's also important, the Cauchy Riemann equations will allow us to prove the complex, and here emphasis on complex differentiability of certain functions such as the exponential function and the logarithm functions. Proving these facts with difference quotients would be very painful with the tools that we have at hand. It would not be impossible, but it would take quite a while to do and would require rather epic computations with difference quotients. And then from the more abstract point of view that we're taking in this course, we'd rather do these epic computations once to construct a tool, namely the Cauchy Riemann equations, and then just keep using that tool. Okay, so what's the theorem? What are the Cauchy Riemann equations? We let f of z being u plus iv of z, and then z is of course x plus iy, so we have f of z as the complex function. If we view this thing in real variable terms, then it's u of x plus iy plus I v of x plus iy, like we've talked about before, and let that be a function on an open domain, and it's supposed to have continuous partial derivatives in the real variables. Then that function is differentiable at z equals x plus iy, if and only if we have that the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y, and the partial derivative of u with respect to y is equal to the negative of the partial derivative of v with respect to x. Now remember, partial derivatives work just like regular derivatives, only that you leave the other variable constant. So the partial derivative of u with respect to x is just a derivative in x where we pretend that y is a constant. The partial derivative of v with respect to y is a derivative in y where we pretend that x is a constant, and so on. Okay, these equations are called the Cauchy Riemann equations. And moreover, we have that the derivative of f at z is du dx at z, so du dx at xy when z is equal to x plus iy, plus I dv dx at that point z. So we're really fluently translating between the complex picture and the real picture here. If we talk about z, z is x plus iy, and that translates to the point xy. And when we talk about a point xy, then by setting z equal to x plus iy, we get back to the complex picture. Okay, the proof, now notice this is an if and only if, so we have to prove that complex differentiability implies the Cauchy Riemann equations, that's the direction left to right, and we have to prove that the Cauchy Riemann equations imply complex differentiability, and that's the implication right to left. Okay, so we assume that the function is complex differentiable, and we just start computing partial derivatives here. du dx at xy. Well, what is that? As a difference quotient, remember, y acts like a constant, which means this is the limit as t goes to x of u of ty minus u of xy divided by t minus x. And now we want to go back to the complex picture, and we realize that this is the real part, where u is the real part of f, and well, then t of x, t plus iy going to x plus iy, well, that's just t going to x because y is a constant here in this picture. And u of ty is the real part of f of t plus iy. U of xy is the real part of f of x plus iy. And t minus x, notice I've just added 0 because we've got a plus iy and a minus. That highlight didn't go too well, minus iy here. So these are the same thing. And now notice that this is a difference quotient for f, even though we don't quite have z going to z0. We've got z just moving along a horizontal line here because y is constant. But still, because the derivative of f is the limit of this thing as z goes to x plus iy, that limit as t plus iy goes to x plus iy is also f prime of z, where z is x plus iy. And now the real part of a complex number is the imaginary part of I times that complex number, and that's just straight algebra. Take a complex number u plus iv. That real part is u. If you multiply that number by I, you get negative v plus iu, and the imaginary part of that is also u. So that is just complex algebra. And now we're just puzzle the whole thing apart again. We have the I here, we've got the imaginary part, and f prime of z, well, that's the limit f of x plus it minus f of x plus iy, x plus it minus x plus iy, where x plus it goes to x plus iy, so now we're approaching along a vertical line, which is fine if the limit works for z approaching x plus, or for numbers in the complex plane approaching x plus iy in any fashion, then it'll certainly also be, the limit will also be f prime of z when we approach along a vertical line. And now, well, now I just pulled the I into the limit. The numerator stayed the same, and in the denominator I cancel those x's and factor out the I, so we get I times t minus y. Notice that now the i's cancel, so this is the limit, and when x plus it goes to x plus iy, that just means that t goes to y, so this is the limit t goes to y, f of x plus it minus f of x plus iy. Numerator stayed the same all along, and then t minus y in the denominator. And remember the imaginary part of f, that's v, right? So this is the limit as t goes to y, v of xt, x here, t here, minus v of xy, x here, y here. And that's the partial derivative of v with respect to y, because now x here, and here, that x is being held constant. So this is dv dy of xy, and that's the first Cauchy Riemann equation. The other equation is proved similarly. We're not going to force our way through that. That may well even again be a homework problem where we just have to make sure that the negative sign comes out the right way, but the approach is exactly the same way as here. Okay, proof of the other direction. So now we're going to assume that u and v satisfy the Cauchy Riemann equation. So we have that du dx is dv dy, and du dy is negative dv dx. And we just try to compute the limit as delta z goes to 0, f of z plus delta z minus f of z divided by delta z. That one is going to be a bit more technical, and it'll require some multivariable calculus as well as the mean value theorem for functions of a real variable. So that's something where you may want to just pull out your calculus book and look that up through the index. But let's first just see how this goes. I mean, if we want to prove that f is differentiable, it's natural to set up the difference quotient. And because all we have available are stuff that relates to u and v and to real variables, it's also natural to realize that with z being x plus iy, delta z would be delta x plus delta I delta y. And so delta z going to 0 is the same as delta x delta y going to 0. And then we have that z plus delta z is x plus delta x y plus delta y multiplied with an I. And again, we're already going to the real variable picture where we look at this as a function of two variables. Z is x plus iy, so we get xy here, and then delta z is delta x plus I delta y. Okay, so what do we have here? We'd like to subtract these two, but again, these arguments are different. Now, this is not a product, but we're still going to use the same trick, because basically when we go into the real variable picture, we can only control change in one variable, not both variables at the same time. So that means we subtract the mixed term and add the same mixed term. And that is all that has happened here. We split the fractions up into two separate fractions. But that's all that has happened in this step. And now, well, now it gets ugly. Because now we realize that f is u plus iv. So f of x plus delta xy plus delta y minus f of x y plus delta y, that'll be u at the first argument minus u at the second argument plus I v at the first argument minus v at the second argument divided by the requisite denominator. And so that means this first line here, that's this first term, and f of x comma y plus delta y minus f of x comma y, that is u at the first argument minus u at the second argument plus I times v at the first argument minus v at the second argument, still divided by that thing. So this second line is just this second quotient all spelled out with the real and imaginary parts. And now, well, now we want to separate this out a bit. Yeah, now we're applying the mean value theorem for functions of a real variable. Notice that y plus delta y is the same argument here as well as here. So that means this first numerator is actually just a function of the variable x on the interval from x to x plus delta x. And the mean value theorem for functions of a real variable says if you have a differentiable function on a real interval, then the difference of the values at the endpoints, x plus delta x and x, is equal to the length of the interval, which is delta x, times the value of the derivative of the function. Well, that's now a partial derivative because this is a function of x, times the value of the derivative at some point in between, and I called that x plus xi sub u, x plus some disturbance for u, where the xi sub u is bigger than 0 and smaller than delta x. Similarly, v, the y plus delta y, is the same in both places. So this is a function on the real interval from x to x plus delta x, and by the mean value theorem, that means this difference is equal to the real derivative, which is now a partial derivative in x because nothing happens in y, at a point in between, so some point x plus xi sub v to distinguish it from the xi sub u, and then y plus delta y, that's just a constant that we're carrying through here, times delta x times the length of the interval. And again, the denominators have not changed and the i's haven't changed. Similarly, the second line, this is now a function where the x is constant. And so this is a function, a real function on the interval from y to y plus delta y. And the mean value theorem therefore says that this is the derivative of the real function, and because we're going in y, that derivative is the partial derivative with respect to y. X is just the constant that is attached to the constant x input that is attached to the function. The derivative, then we take the derivative at a point in between x plus eta sub u times the length of the interval, which is delta y. And here the v is also, x is a constant input, so this is a function of the real variable y on the interval from y to y plus delta y, and we have by the mean value theorem that this is the derivative, which is dv dy of x comma some point in between x plus eta v, where eta is between 0 and delta y, times the length of the interval delta y. Okay, well, that we just know now that that's true by the mean value theorem. We push that over to the next panel. This is just what we had on the previous panel, the last line copied, and because this one I can actually spread across all the way. And well, now, what are we going to do now? Right, now we're going to use the Cauchy Riemann equations, because again, now these don't communicate with each other, but I'd like to express everything in terms of derivatives with respect to x, which means actually the first and second term stay the same. But remember, du dy was negative dv dx, and dv dy is du dx. That's the only thing that's changed here, so we've used the Cauchy Riemann equations. And why do we do that? Well, we do that because we want to ultimately cancel the delta x plus I delta y. Well, I've got a delta x here. I've got I delta y's here, as well as I delta x's here. And so I just need to sort that out the right way. And so that's exactly what's happening in the next step. We've got the du dx now with a delta x as well as with an I delta y, and so that's how I sort those out. And for the dv dx, well, I've got a y on the outside. I keep the delta x and the dv dx here. And then I have a negative. Well, remember, a negative number, negative 1 is just I times I. I put one I here, I put the other I here, and I've got roughly what I want to have. And here is where we're going to omit a significant technicality, and that is basically as delta x delta y go to 0, the x plus cu y plus delta y goes to xy, the x comma y plus eta v goes to xy, the x plus c v y plus delta y goes to xy, and the x comma y plus eta u also goes to xy, but they're never exactly equal, so we can't factor those terms out. These guys will just be approximately equal to the partial derivatives at xy, but that in turn turns out to be good enough so that we sort of can factor out the x plus iy and cancel it, so that this limit actually is du dx xy plus I dv dx xy. Now, physicists and engineers are quite unscrupulous with that. They will just say, well, yeah, this is approximately equal to that, so we can factor out the x plus iy and cancel so that these limits work out. And there's something to be said for being unscrupulous to at least get the right idea, but mathematicians then actually have to go through the exact arguments, and those arguments still take a little bit. But in keeping with the spirit of this course, we want to get the proofs. We want to get the proofs as right as possible. But if something gets seriously technical, we'll still omit it at this stage. Okay, and that's the proof, because we've proved the left to right implication as well as the right to left implication. And so as an example of an application of the Cauchy Riemann equation, well, the function f of z equals z cubed is differentiable on c. We've already verified that with difference quotients. We can also verify that with the power rule for complex valued functions. But let's also take a look at the Cauchy Riemann equations to just see how they work. Well, f of z is z cubed, which is x plus iy cubed, which is x cubed plus 3iy times x squared, plus 3x iy quantity squared, and then of course the I squared gives us a negative here, and then we've got iy quantity squared, and the I squared gives us a negative 1 here, so we get minus iy cubed. Sort the real and imaginary parts. We get x cubed minus 3xy squared plus I times 3x squared y from here minus y cubed from here. And now we can figure out du dx. du dx is 3x squared minus 3y squared. And that's equal to dv dy, I claim. Yes, derivative of the first term with respect to y is 3x squared. Derivative of the second term with respect to y is 3y squared. And so that's dv dy. Similarly, du dy would be negative 6xy, because the first term here goes away. And I claim that that's negative dv dx. Well, the derivative of y cubed with respect to x is 0, so that's gone. And the derivative here is 6xy, and the negative of that is negative 6xy. So that does work out. Basically, that doesn't tell us anything new. But what it tells us is that the Cauchy Riemann equations are consistent with other things that we've derived, and it gives us a first example as to how to apply those equations. We're going to look at another example, namely the function z bar, which will show us that the Cauchy Riemann equations are extremely valuable in showing that a function is not differentiable, because that's where we don't have to mess with certain kinds of limits. And then we'll delve into the polar coordinate version of it. So let's get to it. By the Cauchy Riemann equations here, the final conclusion, f is differentiable on C. Well, that's nothing new. But let's take a look at something new, and that is, okay, well, I think we'll also still look at z bar, but we'll also look at the function f of z equals e to the z, and we say that that's differentiable on z. Well, that is actually new. F of z is e to the z, which is e to the x plus iy, which is e to the x e to the iy, which is e to the x cosine y, plus I e to the x sine y. That's the definition of the function e to the z, the way we've introduced it. And now we would have to deal with difference quotients here. You could see that that can get rather epic. But we can also simply look at du dx, and du dx is e to the x cosine y, because the derivative of the exponential function is itself on the real line, and that is equal to dv dy, because the derivative of that would be e to the x times the derivative of the sine, which is the cosine of y. And du dy is, well, e to the x stays as it is. The derivative of the cosine is the negative sine y, so we get negative e to the x sine y. And that's negative dv dx, because the derivative of e to the x is e to the x, and sine y is just a constant here. So with just knowing enough about how partial derivatives work, we can show in a very efficient way that e to the z is differentiable on C, and that certainly makes the pain for the Cauchy Riemann equations that we had to go through worth it, because otherwise we'd have to do this one with difference quotients and any number of other functions that we may want to prove that are differentiable. Okay, so by the Cauchy Riemann equations, f is differentiable on C. Okay, finally, the function f of z equals z absolute value is not differentiable at any z element C. That's kind of interesting, because on the real line, the function f of z is only not f of x equals x absolute value is only not differentiable at the origin. But this one actually has rather catastrophic failure as a function of complex variables, so that means we're not going to look at z bar, which is just fine with me. But let's take a look at f of z equals z absolute value. Well, z absolute value is the square root of x squared plus y squared, and the imaginary part is 0, so we get plus I times 0. And that means du dx is equal to x over square root x squared plus y squared. And that is not equal to 0, unless x is equal to 0. Then we look at du dy, and du dy is y over x squared, y over square root x squared plus y squared. How does that go? The derivative of a square root function in either case is 1 over 2 times the square root of the inside, and then you multiply with 2x or with 2y, depending on whether you differentiate with respect to x or with respect to y, and then the 2's cancel to get these terms. And so that's not equal to 0 unless y is equal to 0. And so that means f is not differentiable for z not equal to 0, because in that case, the first or the second one is not equal to the corresponding partial derivative of the imaginary part. And as a square root function, f of z is also not differentiable at the origin, because at the origin we would get 1 over 2 times square root 0, which does not exist. Okay, so now we switch to polar coordinates. Whereas the proof for the Cauchy Riemann equation was something that made us work a lot with rectangular coordinates, the proof for polar coordinates will bring back a lot of stuff on coordinate transformations that you also have seen in multivariable calculus. And if you don't remember that, or if you don't remember that fondly, don't worry about it. We'll go through all the steps regarding the chain rule one more time here also. So, revisiting the Cauchy Riemann equations, let's consider f of z, and let's let that be a function on an open domain that does not contain 0, and with continuous partial derivatives in the underlying real variables. But notice that this time around our underlying real variables are assumed to be the polar variables r and theta, because f of z is now f of r e to the I theta, and that means our real part can be viewed as a function that depends on r and theta, and our imaginary part can also be viewed as a function that depends on r and theta. Okay, we will say that then f is differentiable at z equals r times e to the I theta, if and only if r du dr is dv d theta, and du d theta is negative r dv dr. These latter equations are called the Cauchy Riemann equations in polar form. So again, we have something where the various partial derivatives are related to each other. Always the opposites are related to opposites, du dr, dv d theta, du d theta, dv dr. We also have, again, a negative sign stuck in here. And if you remember your coordinate transformations for polar coordinates, and you realize it can't just be straight equations. There's always some factors r that enter the picture. And if you don't remember that, well, the proof will show us how these things enter the picture, and the proof actually is very much a calculus style proof, high-end calculus, but certainly exactly that high-end that we want to hook into with an advanced class such as a first class in complex variables. So let's finish out the statement here. The value of the derivative is f prime of z equals e to the negative I theta du dr plus I d v dr. Well, that part here is probably not too surprising. And then again, because these coordinate transformations always spit out some other functions, the e to the negative I theta should not be surprising either. Not the exact form, but the fact that there is another function should not be that surprising. Okay, let's take a look at that. We first take a couple of preparatory steps, because basically we want to remember that differentiability means that the Cauchy Riemann equations hold. And so essentially our if and only if will be that the polar Cauchy Riemann equations hold if and only if the rectangular Cauchy Riemann equations for du dx and dv dy and all that other stuff hold. And so that means that we need to express the polar variables in terms of real variables so that we can ultimately apply the chain rule. All right, if you don't remember the chain rule at this stage, let's just follow the computations. dr dx is the derivative of square root x squared plus y squared with respect to x, and that would be 1 over 2 times the inside, so 1 over 2 times square root x squared plus y squared, times the derivative of the inside with respect to x. Well, the derivative of y squared is 0, and the derivative of x squared is 2x, and then the 2's cancel, so we just end up with x over square root x squared plus y squared. And now we remember in polar coordinates, x is r cosine theta, square root x squared plus y squared, well, that's terrible highlighting, square root x squared plus y squared is r, so we get r cosine theta over r, so that's just cosine theta. And that's because as we work with these polar variables, we'd like to have these things replaced, expressed in polar coordinates. dr dy, well, that then goes very much the same way, right? This is and this is then how often also engineers and physicists argue, and rightly argue, this thing is symmetric in x and y, so wherever we had x before we get y, and that means this derivative must be y over square root x squared plus y squared, where here technically those two would switch, but that doesn't do anything. And now we remember that y is equal to r sine theta, and dividing by r then should give us sine theta here. D theta dx, what was theta? Theta was the arctangent of y over x. Derivative with respect to x, well, what was the derivative of the arctangent? The derivative of the arctangent was 1 over 1 plus whatever is inside squared, so we get 1 over 1 plus y over x quantity squared. And then because we're differentiating with respect to x, we have to differentiate the inside with respect to x, and so that gives us, because y is a constant, negative y over x squared, because the derivative of 1 over x is negative 1 over x squared. Alright, so we keep the negative sign out front, multiply with the x squared in the denominators to get negative y over x squared plus y squared. Y is r sine theta, and x squared plus y squared is r squared, so we get negative sine theta over r. So this is just a really good exercise in working with polar coordinates. If you want to, you may want to stop the presentation right here and see if you can work out d theta dy for yourself. Of course, I'll just go ahead and continue. That would be the derivative with respect to y of arctangent y over x. And so that is, again, by the chain rule, 1 over 1 plus the inside squared, 1 over 1 plus y over x quantity squared. And the derivative with respect to y of y over x, of course, is a whole lot simpler. That's just 1 over x. Well, 1 over x is x over x squared. So that means we get here that this is x over x squared times all this stuff, which is x squared plus y squared. X was r cosine theta, so this ends up being cosine theta over r. Okay, first preparatory step done. We still work with preparatory steps because now we want to figure out what du dx is, and we want to express that in terms of those corresponding polar derivatives. In order to do that, we use the chain rule, and the chain rule says whenever you've got two coordinate systems and you differentiate your function with respect to a variable in one coordinate system, what you have to do is you have to take the partial derivatives with respect to all the variables in the other coordinate system. So that would be partial derivative with respect to r, as well as the partial derivative with respect to theta. And the partial derivative with respect to r is multiplied with the partial derivative with respect to of r with respect to x. And the partial derivative with respect to theta is multiplied with the partial derivative of theta with respect to x. So if you were to pretend you were canceling, you'd be getting du dx's back, but because you're using a multivariable chain rule, this is not 2 du dx. This is really just du dx. And the reason why that works lies in the proof of the chain rule, which is another rather sophisticated part of multivariable calculus. It is something, look up the chain rule if necessary in your multivariable calculus text, and we just apply it here. Okay, and now we know, because dr dx is cosine theta and d theta dx is negative sine theta over r, we get this expression. And the advantage of this expression is that this is an expression that is purely in terms of the polar variables. Okay, so now you can already anticipate how that continues, because now we're going to express dv dy in the same way. So what's that going to be? dv dr, dr dx, dv d theta dx, right? And dr dy then was sine theta, and d theta dy was cosine theta over r. And so we're just substituting those, and we get a polar expression for dv dy. du dy, well, same story. du dr, dr dy, du d theta dy, and then dr dy is sine theta, d theta dy is cosine theta over r. Just go back to the previous panel. Here's one of those situations where you may want to open up the slides as well as the video presentation just so you can do your cross-referencing. And then dv dx, well, that's dv dr, dr dx, dv d theta dx. dr dx is cosine theta, d theta dx is negative sine theta over r, and that means we've got polar expressions for all the derivatives in the rectangular coordinates. And so now we can prove one direction. We can prove that the polar Cauchy Riemann equations imply the rectangular Cauchy Riemann equations. So the polar Cauchy Riemann equations are r du dr dv d theta and du d theta equals negative r dv dr. And here's where you want to use a piece of paper or just follow very, very closely, because I claim that this implies, by direct substitution, that du dx is dv dy. Well, let's see. Du dx is here and dv dy is here. These are the expressions that we want to focus on. Okay, if du d theta is negative r dv dr, then this becomes negative r dv dr times sine theta over r with a negative sign. Okay, the two minus signs cancel, the r's cancel, and so we keep just the dv dr and the sine theta, and that's exactly what we have here. And if dv d theta is equal to r du dr, it's just a matter of reading it the right way, then we get, for this dv d theta, r du dr, the r's cancel, and so we end up with du dr cosine theta, which is exactly what we have here. So that means by direct substitution we really get du dx equals dv dy. And I also claim we get du dy equals negative dv dx. Okay, again, good point to maybe stop the presentation and see if you can work it out for yourself. Let's go through this very carefully, and if necessary you work it out with paper and pencil. There's no shame in doing that, but let's see. I mean, the more we can do mentally here, the more things we can keep track of in our minds, the easier this stuff becomes. And it's a very peculiar type of memory, because we're not trying to memorize this forever. We're just trying to keep track of it. So it's not peculiar, it's short-term memory essentially. Okay, so if dv d theta is r du dr, well, then this is r du dr. So the r's cancel, so we end up with negative du dr sine theta, which is the negative of the first term. And that's okay, because we want it to be the negative of that first term, right? And if du d theta is negative r dv dr, well, then this thing here is negative r dv dr. The r's cancel, we get negative dv dr cosine theta, which is the negative of this one. And so that means this equation here is verified too. Outstanding. Conversely, if du dx is dv dy, so now we're already proving that the rectangular Cauchy Riemann equations imply the polar Cauchy Riemann equations. So if du dx equals dv dy and du dy equals negative dv dx, well, that means this thing is equal to this thing, and this thing is equal to the negative of that thing. And then just setting those equal to each other, we obtain the following. We obtain du dr cosine theta plus du d theta negative sine theta over r is dv dr sine theta plus dv d theta cosine theta over r, and du dr sine theta du d theta cosine theta over r is negative dv dr cosine theta plus dv d theta sine theta over r. Again, just go back to the previous panel and verify that that's just setting the corresponding terms equal to each other. Well, that's a system of equations. And now, if we take the first one and multiply it with r cosine theta, and if we take the second one and multiply it with r sine theta, well, let's see. That would mean I multiply this with r cosine theta, I get r cosine squared theta du dr. I multiply this one with r sine theta, and I get r du dr sine squared theta. And then, because cosine squared theta plus sine squared theta is equal to 1, this term and this term multiplied the right way give us the r du dr. If I multiply this one with r cosine theta, I get negative du d theta sine theta cosine theta. And if I multiply this one with r sine theta, I get du d theta sine theta cosine theta. And this negative sign makes sure that these two guys cancel, which means these two left sides here add up to r du dr. If I multiply this one with r cosine theta, I get r dv dr sine theta cosine theta. Multiply this one with r sine theta, I get negative r dv dr sine theta cosine theta. So this guy and this guy will cancel. And if I multiply this guy with r sine theta, no, with r cosine theta, top with r cosine theta, I get dv d theta cosine squared theta. Multiply this one with r sine theta, I get dv d theta sine squared theta. And if I add that up, then sine squared plus cosine squared gives us 1. So I get dv d theta here. And similarly, multiply the first with negative r sine theta and the second one with r cosine theta. This is really just the elimination method for systems of linear equations, very much on steroids, because we of course work with rather ugly coefficients, but it gets us the right thing, right? Multiply the first one with negative r sine theta, gives us negative r du dr sine theta cosine theta. Multiply the second one with r cosine theta, we get negative r du dr sine theta cosine theta. This guy and this guy cancel. Multiply the top here with negative r sine theta, we get du d theta sine theta squared, sine squared theta. And the second one with r cosine theta, we get du d theta cosine squared theta. Cosine squared plus sine squared is 1, and we get just du d theta left over from the left side. Multiply the right side, the first one with negative r sine theta. That gives us negative r dv dr sine theta. Multiply the second one with cosine theta, gives us r cosine theta, gives us negative r dv dr cosine squared theta. Sine squared plus cosine squared is 1. We get negative r dv dr. Multiply this guy with negative r sine theta, we get negative dv d theta sine theta cosine theta. Multiply this guy with r cosine theta, we get dv d theta sine theta cosine theta. So that means we've got the negative here and the positive here, so those cancel. So what remains from the right side is negative r dv dr. So that means that, and so this shows that f is differentiable if and only if the Cauchy Riemann equations in polar form are satisfied, because those are equivalent to the Cauchy Riemann equations in rectangular form. We omitted the technical part, which is that the continuity of the partial derivatives in one coordinate system gives their continuity in the other. That's another thing that I would want to leave for a more advanced class. And so now we turn to the formula for the derivative. And well, the derivative f prime of z is du dx plus I dv dx. And that's du dr cosine theta plus du d theta negative sine theta over r. And that's from our computation of du dx. And then plus I times the computation of dv dx. Okay, that's one I know it's right because I did a cut and paste here. Go back to the panel and verify that that really is what we wanted it to be. And so now, well, now we'd like to get this in terms of du dr and dv dr, and remember that du d theta is equal to negative dv dr times r, so that means the minuses and the r's cancel. And here we have the d, and so the first term stayed the same. Here we have dv dr, so that stays the same. Dv d theta was r du dr, so this ought to be right. This is dv dr cosine theta du dr. The negative sign is still here, and the r has canceled, so we get negative sine theta. And so now the question is, how do we pull all that stuff together? And how do we just pull out something so we get a du dr plus an I dv dr? Well, this one doesn't have an I here, but we could get that with a negative sign. But the only way we can generate a negative sign is by saying that this guy here is I squared times negative 1, and then the I squared is broken up as I times I, and the negative 1 is pulled into the sign as a sine negative theta. So that gives us the transformation of this term into this term, gives us the idea that we need negative thetas. Well, for this term to this term, that's not a problem because cosine theta is equal to cosine negative theta. Then we have This third term here, dv dr cosine theta, well, that's just I dv dr cosine negative theta, because cosine negative theta is cosine theta. And that leaves us with I times this term, and negative sine theta is sine negative theta. So we get du dr I sine negative theta, and so this term is this term. So again, the idea came from the fact that we somehow have to finagle a real and an imaginary part where we can factor out a du dr or a dv dr, which means we had to shove this dv dr into the imaginary part. That's what got us from this second term to this third term here, and then we just verified that all four terms are still here as we go from this line to this line. Hang on, somebody knocks. Okay, somebody knocked. I got it taken care of. Let's see. We had just verified that we can go from this third line to this fourth line, and we can see the light at the end of the tunnel here because we can factor out the du dr and the dv dr. We have, on account of this I and this I, well, here we're actually going to factor out an I dv dr. And if we notice what's left is cosine negative theta plus I sine negative theta, cosine negative theta plus I sine negative theta. So what we factor out actually is an e to the negative I theta, and we have the du dr and the I dv dr here. And that was the formula that we claimed. All right, that was again quite demanding, but now note that we very quickly get out of that the square root function, as well as in the next example, the logarithm function, are differentiable on sets on which they're continuous. So the square root function r to the 1/2 e to the I theta half is differentiable on any set r greater than delta, where delta merely needs to be greater or equal than 0. I think that's something that I ought to insert there. And there it is. And our angle theta must be so that alpha is smaller than theta is smaller than alpha plus 2 pi for any alpha. Basically, we can't wrap all the way around the origin, because then the argument increases. For the square root function, that's not that bad, but still, otherwise we'd be encountering things like Riemann surfaces, which we'll talk about later on in the course anyway. It's just cleaner to do it this way. Well, yeah, now we verify that f of z is r to the 1/2 e to the I theta over 2, which is r to the 1/2 cosine theta over 2 plus I r to the 1/2 sine theta over 2. Well, r du dr, that would just be r times 1/2 r to the negative 1/2 cosine theta over 2, which is 1/2 r to the 1/2 cosine theta over 2, and of course that is dv d theta, because the derivative of the sine is the cosine, and the 1/2 comes out from the chain rule. And negative r dv d r, well, that would be negative r times 1/2 r to the negative 1/2 again. That's just the derivative of r to the 1/2 times sine theta over 2, because theta is a constant with respect to r. That's negative 1/2 r to the 1/2 sine theta over 2, and that's du d theta, because the derivative of the cosine is the negative sine, and the 1/2 comes out via the chain rule. Okay, so that means this function satisfies the Cauchy Riemann equations in polar form, and that means that this function is differentiable. Okay. Yeah, and the reason why we can't wrap all the way around is we would get a discontinuity wherever we cut here. Okay, similarly for the logarithm the discontinuity is a bit more obvious. Take the function f of z equals f of r e to the I theta, being ln of r plus I theta. That's really what we would get if we took the logarithm and just apply the logarithm laws that we know as if they did work. Turns out they do, but we haven't formally justified them yet, because we haven't formally introduced complex logarithms. But this function is differentiable as long as r is greater than some delta, which is greater or equal than 0. So it could even be just r greater than 0. And again, theta can't wrap all the way around, and that's much more obvious here, because if theta goes all the way around by 2 pi, then from one direction we would approach alpha, and from the other direction we would approach alpha plus 2 pi, so that thing would be highly discontinuous then. Okay, well, f of z equals ln r plus I theta. Well, that turns out that r du dr is just r times 1 over r, which is 1, and that is the derivative of v with respect to theta. And negative r dv dr, well, that's 0, and that's du d theta, and so that's the derivative of this function, which will ultimately be the logarithm function, or actually a branch of the logarithm function for us. I think the next thing is analytic functions. I mentioned that we would take a break. Certainly, we have worked long enough here. By my clock, it's 11:52. I'm still a growing boy. It's time to eat lunch. So we have f of z as the complex function. If we view this thing in real variable terms, then it's u of x plus iy plus I v of x plus iy, like we've talked about before, and let that be a function on an open domain, and it's supposed to have continuous partial derivatives in the real variables. Then that function is differentiable at z equals x plus iy, if and only if we have that the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y, and the partial derivative of u with respect to y is equal to the negative of the partial derivative of v with respect to x. Now remember, partial derivatives work just like regular derivatives, only that you leave the other variable constant. So the partial derivative of u with respect to x is just a derivative in x where we pretend that y is a constant. The partial derivative of v with respect to y is a derivative in y where we pretend that x is a constant, and so on. Okay, these equations are called the Cauchy Riemann equations. And moreover, we have that the derivative of f at z is du dx at z, so du dx at xy when z is equal to x plus iy, plus I dv dx at that point z. So we're really fluently translating between the complex picture and the real picture here. If we talk about z, z is x plus iy, and that translates to the point xy. And when we talk about a point xy, then by setting z equal to x plus iy, we get back to the complex picture. Okay, the proof, now notice, this is an if and only if, so we have to prove that complex differentiability implies the Cauchy Riemann equations, that's the direction left to right, and we have to prove that the Cauchy Riemann equations imply complex differentiability, and that's the implication right to left. Okay, so we assume that the function is... Welcome back. Well, after we have investigated differentiability from the point of view of difference quotients, as well as from the point of view of differentiation formulas, there is yet a third way in which differentiability can be investigated for functions of a complex variable, and that is through the Cauchy Riemann equations. So we're going to talk about the Cauchy Riemann equations. We're going to talk about those equations in polar coordinates. And once we have these results, we will derive some consequences for analytic functions. Remember, analytic functions are complex differentiable functions. And we're going to talk about functions that are called harmonic functions. Those are functions so that the sums of their second partial derivatives are 0, and those functions are very important in applications. Now, the proof of the Cauchy Riemann equations will be probably the most technical proof that involves difference quotients in this course, and the proof for differentiable functions, and a new way to look at certain real differentiable functions, namely at the real differentiable functions that satisfy the Cauchy Riemann equations. Finally, and that's also important, the Cauchy Riemann equations will allow us to prove the complex, and here emphasis on complex differentiability of certain functions such as the exponential function and the logarithm functions. Proving these facts with difference quotients would be very painful with the tools that we have at hand. It would not be impossible, but it would take quite a while to do and would require rather epic computations with difference quotients, and then from the more abstract point of view that we're taking in this course, we'd rather do these epic computations once to construct a tool, namely the Cauchy Riemann equations, and then just keep using that tool. Okay, so what's the theorem? What are the Cauchy Riemann equations? We let f of z being u plus iv of z, and then z is of course x plus polar coordinates, will require a lot of coordinate transformations. So on one hand, we need to brace ourselves, but the good news is, of course, that these are good exercises, and the other good news for you is that this is the last really technical proof, at least for a while. And the good news for me is that after we're done with polar coordinates, I'm going to eat lunch before I'll talk you through the analytic functions and the harmonic functions. So let's take a look at this stuff. Basically, even though all the computations for differentiability work rather well with complex numbers, we've seen that those computations really were just the same computations as what we did in for functions of a real variable in calculus. It would be nice to also have an idea what complex differentiability means in terms of real functions of real variables. And well, the Cauchy Riemann equations provide just that. And as such, we will obtain a new way to look at complex